All right, hello. My name is Andrew Liu. I'm a PM on the Azure Cosmos DB team. And today we're going to be taking a look at Azure Cosmos DB. We're going to look at some of the design patterns and case studies. This is going to be a technical session. I'm hoping you are all technical folks. Can I get a raise of hand on if you're a technical person? Awesome, you are in the right place. So I'm going to just do a very, very quick recap of what Azure Cosmos DB is for those of you who have not been able to attend any of our other sessions. We're going to go over some of the common scenarios as well as the architectures for those scenarios and how you would build a solution on Azure Cosmos DB. We'll go into some of the partitioning design, and if there's one thing you take away from this session, honestly, partition design is the most important design aspect of consuming Cosmos DB. So do pay attention for that one. Once we conclude partition design, we'll talk a little bit about the change feed, which is an awesome, relatively new feature that we've exposed through Cosmos DB. And that is going to be incredibly useful for building event-driven architectures and doing event sourcing. I have a few special guests from ASOS.com with me here. We'll be doing a technical deep dive into how they have built all of their microservices on Cosmos DB. And then at the end of this session, we'll leave some time for Q&A. So don't be shy to ask questions. A very quick overview of Azure Cosmos DB, like what is this thing, in case you haven't seen it already. It's Microsoft's globally distributed multimodal database service. And you can think of this as, I like to think of this as on the very, behind all of the marketing, behind all of that stuff, like what does the core platform really boil down to? And the core platform is actually a distributed database that offers turnkey global distribution, the elastic scaling of storage and throughput, predictable performance, well-defined consistency models, and this is built as a fully managed service with comprehensive SLAs. On top of this distributed database, we are actually able to represent several different data models on top of it, ranging from key value, column, family, document, and graph data models. And these are exposed through a variety of different APIs, including a document DB, SQL, and JavaScript API, a Gremlin API, a table API, and a MongoDB API. Now, let's take a look at some of the things that people have been building on top of Azure Cosmos DB. And if I were to just kind of take a look through all of our users, like our top users, and kind of get a survey of what are people building, are there any kind of commonalities? And in fact, there are. And a few of the areas that have really popped, I found, are an IoT for building systems for capturing telemetry and sensor data. And the reason why Cosmos DB is popular in this space is mostly because as a distributed database, it can absorb and sustain a very, very high amount of write ingestion coming in. So we're talking here, like if you have, let's say, a million servers deployed, a million sensors deployed, each of them emitting the state going, here's my data, here's my data, here's my data, here's my data. Like at the end of the day, these devices generate so much more data than humans can. Like even like Mr. Trump, the guy is always on Twitter. Like how many tweets can he actually pump out a day? He's not actually tweeting every second of every minute of every hour of every day for every year, right? But sensors can do this. And so if you are, let's say Toyota, when you have millions of vehicles on the ground driving, emitting telemetry back into a database, how do you actually capture all of this? On top of this, each generation of device you have out there, it turns out it's a lot easier to update software than it is to update hardware. And as each generation of hardware you launch out there, you're going to deploy additional sensors, different sensors, and as a result, the workload, the data coming in, is going to be increasingly heterogeneous. And as a result, you also want something that has a flexible data model, and you can serve low latency queries back out off of the data being captured in. So a common pattern here is you basically, I'm guessing if you guys have heard of the Lambda architecture pattern, basically what you do is you divide up a hot path and a cold path. And for the hot path, this is where Azure Cosmos DB really fits in. because of its ability to capture a high amount of write ingestion coming in. And so what you typically will do is you'll have messages coming in through something like IoT Hub. IoT Hub is not only just a nice message buffer for IoT devices, but it also establishes a two-way communication channel back to the device so that you can actually control the device. From here, as this comes in, you can process this using a stream processor where you can put aggregates into a code store for archival or for powering a real-time analytics dashboard, while the raw telemetry comes into Cosmos DB. And what this allows you to do is not only see, hey, I have seen, let's say, a spike in my telemetry off of the real-time aggregate, but then I can double-click and then query into Cosmos DB and understand why. Why did that anomaly happen? On top of this, with the Cosmos DB change feed, you can also set up subscribers that when you see something, let's say, an anomaly, you can also react. So let's say if we have a refrigeration scenario and we have a bunch of goods being manufactured and they have to be refrigerated. If you see the temperature starting to rise, what you want to do is react quickly. You don't want to just stare at a dashboard and go, oh, it'll be a shame if my goods spoil. Instead, what you want to do is immediately tell IoT Hub, hey, kick in that backup refrigeration unit so that my goods don't spoil. We also see a lot of usage in e-commerce. And in this space, I mean, we have challenges around seasonal traffic, around Black Friday, around delivering very, very low latency, rich experiences down to our end users. When you're talking about things like product catalogs, orders, events, having a schema-agnostic store is also a very, very critical capability. And as well as when you have a global user base, I mean, having a global presence and being able to globally distribute a single data set all around the world become very, very core needs. A few of the areas that we see usage are retail product catalogs, powering real-time recommendations for its low latency capabilities, as well as powering retail order processing pipelines. And I'm going to kind of skim through this quickly because what we'll be doing is a technical deep dive, really kind of drilling down into how ASOS uses Cosmos DB in the latter half of this presentation. Another area we see a lot of usage is in multiplayer gaming. And gaming is kind of an interesting industry, mostly because the scalability, what you need, tends to be a little bit different from every other industry. If you're, let's say, building an IoT scenario or e-commerce scenario, typically what happens is your business grows over time, your request volume grows over time, your data volume grows over time. However, for most games, games are a bit more seasonal. And what you see is for games, not a lot of consumers really like to play like old games, right? Like 20-year-old games, 10-year-old games. Games don't actually really age that gracefully. What ends up happening is on day one, when you launch, you need to be able to scale to handle all of that request traffic coming in. And if you fail to do so, then you end up with a very high-profile failure. Your Metacritic reviews, your Steam reviews will look terrible. And it's really, really hard to recover. So being able to scale on demand to handle bursty traffic on day one is one of the core reasons why we see also a lot of usage on Cosmos DB in the gaming space. But also, when you're dealing with multiplayer games, if you ever have played a multiplayer game where the latency is very high, you quickly find that the game is unplayable. And so also being able to deliver very, very low latency queries is another core capability why we see a lot of usage in the gaming space for Cosmos DB. And with Azure, I mean, we give a very expensive toolkit for both globally distributing your static assets via a CDN, as well as your dynamic, constantly changing data, your social and multiplayer data in Cosmos DB, on top of which we have strong analytical capabilities with HD Insights, as well as the ability to event off of certain events coming in through the Azure functions. So let's take a look at, okay, those are some of the common use cases for Cosmos DB, but now let's take a look at, well, how do I actually build a solution on Cosmos DB, and what are the things I want to think about? And the first thing you want to think about is how do you design your partitioning strategy? And to give you some context on how partitioning works with Cosmos DB, Cosmos DB has this concept of containers. These are going to be your collections, your tables, your graphs, for which this is actually going to be a logical abstraction. These containers can scale from a small amount of RUs to a very large amount of RUs. These are the compute for serving requests per second. Think of this as throughput. They can also scale from gigabytes to petabytes by elastically scaling out. So by virtue of scaling out, how do we actually scale out? The key thing that you'll want to pay attention to is when you create a container, you're going to have to define a partition key. So what is this partition key and why is this so important? The partition key is actually the logical abstraction. It's the hint for how should Cosmos DB distribute the data for a container across all of the underlying machines. For Cosmos DB, what we're doing here is we're not actually tying an instance to a machine, but rather an instance can actually span many, many machines. And if we're going to be distributing the data as well as the requests across those machines, we basically need a hint for how to distribute that data as well as those requests. So the partition key is going to be a logical partitioning abstraction. And in this example, what we might use is something like, let's say, a user ID. What happens behind the scenes is that partition key will get hashed, and this will be distributed over a very, very large range of possible values. And by taking this consistent hashing-based approach, what we can do is we can then carve those ranges out and to subdivide them over physical partition sets. These partition sets, the number of partition sets can be variable and tuned based off of your actual storage and throughput needs. And this way, because we choose a frugal number of partition sets underneath, we can both give you scalability while still giving you a low total cost of ownership. Basically, what we'll do is we'll co-locate a range of partition keys on each physical partition. So what happens when a partition now needs to grow? What we can do is also we can dynamically subdivide those ranges so that if a partition starts filling up, what we can do is while the database is still online and serving requests, what we can do is we can split that partition and put half of that range in one subpartition as well as the other half into another partition. And this allows your database to kind of seamlessly grow as your application grows while also maintaining high availability while doing so. So what's really nice about this is if you've ever had to shard or partition your own databases, what you found is the management of these partitions is really, really difficult, especially when you want to maintain high availability. But because we have taken all of the best practices learned over the years and baked it natively into the system, and partition management is completely taken care of on behalf of users by the database service, then you don't actually have to worry about this. Instead, the database just seamlessly grows as your application grows. Now, how do you choose a good partition key? Like, what are the things that you want to think about? And at a high level, you have basically two goals. Number one, you want to distribute the overall request volume and the overall storage across as many partition keys as possible. This is your mechanism for scaling. And what you want to do is you want to choose an even distribution that avoids hot partition keys. So an example of a poor partition key is if you have a telemetry scenario where you are partitioning off of the current time. At any given time, all of the requests coming in will have the exact same current time. And what that means is that you're going to have a very hot partition, leaving all of the other partitions idle. A good partition is something where all of the requests coming in are fairly evenly distributed. So for a multi-tenant system, it typically, multi-tenant systems scale by the number of users. So having something like akin to a user ID, or for IoT, because you're scaling by the number of devices, having something akin to a device ID tends to be a fairly natural partition key. The other design consideration you want to think about is you want to avoid blind fanouts for queries. You want to be able to route those queries efficiently so that when you query the database and look for a piece of information, you have to touch the minimal number of partitions needed while not having to blindly look at all of the other partitions. And so what this means is that in the where clause or in the filter of your queries, you want to choose a partition key that can be easily represented in your queries. So how do you actually, given these design goals, how do you actually replicate this and set yourself up for success? The things that you want to first think about are, first, ballpark the scale needs. How much size and how much throughput, how much storage and throughput do you actually need. And the reason why you want to look at this first is this will also have this will determine the number of underlying partitions, and as a result, it'll also tell you how much you need to be concerned about things like fan-out. If let's say I'm running a 2-partition system, fan-out is really not that bad. However, if I'm running 1 million partitions and I have to blindly fan-out to all of them, then this is going to greatly amplify the cost of each of my requests that need to fan-out. I'm going to run into scalability concerns. Now, once you have kind of determined and ballparked the scale needs of your workload, you'll want to actually deeply understand the nature of the workload itself. And specifically, what you want to do is you want to divide up the read path and the write path. You're going to want to take a very, very close look at that. And the reason why that is writes and reads naturally tend to move you into different ends of the spectrum. For writes, each write request coming in, it's very easy to just go for design goal number 1, which is distribute the overall request volume, because you don't have to worry about fan-outs ever. And so this leads you towards choosing partition keys that are very, very fine-grained in nature. Meanwhile, if you have a read-heavy workload, what you'll often find is that to make queries easier and to avoid having to blindly fan-out, you choose coarser partition keys so that you make it easier to represent that partition key as part of your query filter. So what you want to do is, once you have understood kind of the read and write ratio, you want to optimize around what is the bulk of your workload. Use the Pareto principle, the 80-20 rule, and don't sacrifice performance on the 20 for the 80. Or I mean, rather, sacrifice performance on the 20 and optimize for the 80 as opposed to the other way around. Now, when you're looking at reads, what you want to do is also you want to understand your top queries. It can be your top 3 queries, top 5 queries. Look for common filters. This will give you a lot of hints on what would be a natural partition key for a read-heavy workload. And for writes, really just understand the ratio of inserts and updates. This will have a little bit less of an impact on the exact partitioning scheme, but it'll have a large impact on your object model. And so this is something that you also want to take a very close look at. So some general tips. Don't be afraid of having too many partition keys. It's a completely logical abstraction. And I mean, the more partition keys you have, basically the more underlying partitions can back your container, and as a result, you get more scalability out of it. Now, one of the interesting features that we recently launched with Cosmos DB is the Cosmos DB change feed. And basically what we have behind the scenes with Cosmos DB is a completely latch-free database that uses log structuring techniques for persistence. And because we are basically appending to a log as writes come in over and over, what we can do is we can assign log numbers to the writes coming in and expose them back out via a change feed, in which the change feed is basically a persistent log of those records that is exposed in the order the records are actually modified, or by LSN order. And so this can be used for a variety of different scenarios, from event sourcing to microservices, materializing views, as well as replicating data. And we're going to actually talk a lot about each of these different use cases with the ASOS technical deep dive. But some of the things to help gear yourself up for context on how to work with the change feed. Remember, I just told you each container is runs on a number of partitions. And so what you basically have is a log per partition range. And as you attach consumers, you're going to want to read from each of these different partition key ranges. The code for this is actually quite simple. We expose an API called read partition key ranges. As you grab all of these partition key ranges back, what you want to do is, for each one of them, just read the feed of changes coming back out. In the common case, this is actually very easy to implement. However, there's a few edge cases that you're going to want to think about. And specifically, those edge cases are going to be what happens when your partition starts to grow and, let's say, split. So what we've done is we've actually built a convenient library called the change feed processor library. And what it does is it'll actually allow you to scale out a number of subscribers. And what it does is it basically creates a concept of leases. And these leases will get stored into a side collection. And what we have is basically a greedy algorithm where each of these hosts is going to try to grab a lease on every one of the underlying partitions. And it's also going to do all of the exception handling for you so that if an exception, let's say, decides it needs to grow and split, it'll automatically grab a lease on the child partitions and resume execution. So all of that will happen behind the scenes, making this a very convenient way for consuming the change feed. For the change feed processor library, all you need to do is, as changes come in, what it'll do is it'll call the process changes async function. So basically, you're going to implement an interface, and you're going to implement the process changes method. And then once you've registered, or once you've implemented that method, you register your change feed observer to the actual event host. And this is what's going to attach to the container that you want to subscribe to, and basically grab a lease onto all of the underlying partitions or fight for those leases across against other change feed hosts. So with that said, let's take a look at event sourcing with Cosmos DB at ASOS. I have a few guest speakers here, Andrew Potts and Mike.
Thank you, Andrew. Hello. Right, well, let's start anyway. Hello, everybody. My name's Andrew Potts. I'm a solution architect at ASOS.
And I'm Mike Gore. I'm a solution architect at ASOS on the payments platform.
We're very grateful to be invited here today. Today we're going to talk to you about how we use Cosmos DB within ASOS. So we're going to talk about Cosmos DB, the change feed. We're going to talk about how we use event sourcing as a pattern within our system. And then we're going to show you a little bit about Azure Functions, the new announcement that Microsoft have made this week. So let's start with who are ASOS. ASOS is a fashion company. Its goal is to be the #1 fashion destination for 20-somethings. We're online only. We have no physical stores. So we engage our customers through the website, through our native mobile apps, and through our social media. We sell all around the world. We deliver to over 200 countries, and we have fulfillment centers in the UK, in Europe, and the US. We're adding new sites all the time in order to give our customers more personalized products and promotions to match the seasons and styles in which close to where they live. We're a company that works at great scale. Currently, today, we probably have about 85,000 ASOS and branded products on our site. We add and remove maybe 4,000 items every week. We have 15 million active customers, and they're generating about 100 million page views per day. I work in the order management technical team. It's our responsibility to take an order from booking all the way through to delivery to your door, and we also deal with the returns process as well. Black Friday, Cyber Weekend is always a very busy time for us. It's our busiest period. Last year, during Black Friday weekend, we received 893 product requests a second at times. Over the 4-day weekend, over 4 days of the Cyber Weekend, we received 2 million orders, and at times we were processing 33 orders a second. And for us, this is predicted to be even bigger this year. So the challenge we have is we're a global retailer operating at global scale, and we need to make sure that we can provide our customers with a consistent experience, irrespective of whether you live in Australia, the US, or Europe. In order to do that, a couple of years ago, we took the strategic decision to move to the cloud. We selected Microsoft as our technology partner, and we're using Azure. I overclicked there. So we went to the cloud, and as part of that, we selected Cosmos DB for our new systems. Why did we do that? Our previous systems were on-premise in a data center, and we used, in order management, it's a workflow-based system, so we used event sourcing, and we used a document database to store our events. So our natural conclusion was to look at Cosmos DB because it supports the document model. But moreover, there's obviously great benefits to using it being PaaS. Now we don't need to worry about software updates, SAN upgrades, monitoring the disk capacity. All of that's taken away from us. It gives us predictable usage through the RU model that Andrew spoke about earlier. You pay for your requests per second effectively. Now we can predict how many orders we're going to be receiving, so we can We can plan for and measure how many orders, how many RUs we need to purchase. And when it comes to peak, when it comes to November this year, and we go through Black Friday again, we can ramp that right up. We can make sure that we're not going to fail as a system. And then we can bring it back down afterwards to save some money. The scaling's good. Geo-replication is very important for us as well. You know, we've got customers all around the world, so we need to give them a consistent experience. Now with Cosmos DB, you can provision it all around the world. That means we can put a database close to our customers, which means if they're hitting our APIs, they're not doing long writes across continents. Also, the geo-replication is good. The data is being moved all around the world, so if there is a region failure, we've got some data resiliency. We know our data's safe. The SLAs are good, 99.99% on availability, and you get SLAs on throughput, latency, and consistency. And as Andrew was alluding to, the change feed for us was an absolute game changer. When we were looking at how we could do event sourcing in the cloud, when we learned about the change feed, it was fantastic. We adopt a reactive microservices architecture, so we have lots of lightweight, small components doing one thing. They listen to an event, they do some work, and they emit an event. And we plug all of these together, and that builds our workflow. Now, with the change feed, well, these events, I should say, are stored as documents in an event store. With the change feed, we can listen to these events as they're emanating in the system. The services are writing events. We can listen to these events and trigger new workflow. Right now, we're working on a new project at which Cosmos DB is at the heart of it. It's called Returns Express. And what we're doing here is we're providing a new feature for our customers. This is going to allow them to return their goods online. So you've bought 10 pairs of jeans or 3 pairs of jeans and you want to return 2 of them. What you can do now is using your app and using your website, you'll be able to book the return online, download the delivery label, and then you get refunded. So there's a workflow going on there, and at the heart of that workflow is Cosmos DB. So we look at the diagram here, what we're showing is it's a game of 2 halves from our perspective. On the left-hand side of that diagram, what we want to do is provide an API to the client that's very responsive. So we can put Cosmos DB in various regions, and we have a very short write. What we'll do is just take that request from the client and save it into Cosmos DB. Here, we're preferring availability over consistency. When we move to the other side, the right-hand side, we're all about consistency. You need to make sure you're only processing an order once. You don't want to be doing 2 things to that order. So what we need to do is take that data that we're emanating from the regions and bring it over into our single data, single region over there, which is acting in an active-passive mode. So what we're going to do now is go through go a bit more into detail into 4 use cases. The first one is booking that return, the left-hand side, the client submitting a return into Cosmos DB. Then we're going to talk about processing a return, which is the right-hand side, how we use event sourcing to monitor and the flow of the return through its journey. Then we're going to talk about how, as a service, we might integrate with other systems, other internal systems, such as payments or delivery. Finally, we're going to show how we re-index the data that we have in Cosmos DB, because in the right-hand side of that diagram, it's partitioned by return reference. When we're talking to customers, when they're going to their My Account screen, it needs to be indexed by customer ID. So we need to take all of that data and re-index that, and we'll show you how we can do that using Cosmos DB change feed. So firstly, we're going to do use case 1, which is booking a return. This is somebody booking a return, they've bought some items and they want to send them back to ASOS. Our requirements are this. We want to be able to take bookings from all around the world. We need to respond as quickly as possible. We want the highest level of SLAs. There's nothing more frustrating than, preparing your return online on the screen, hitting the submit button and then it not responding. We need to be able to scale up and scale down as required. And then finally, we need to handle the scenario where a connection may be unreliable. I'm often on a train now and I look over and I see people on the little ASOS app buying stuff or returning stuff. So trains and tunnels are our biggest enemy, really. You're on a train, you're about to hit the submit button and you go in a tunnel. The response is lost, the client retries. We've got to handle idempotency and handle that scenario where we might get 2 or 3 requests for the same return. Now, this is a previous design we had. This was more around the order system. This was our first approach about how do we take orders, how do we receive orders. So we'd have APIs all around the world, and we'd basically take the request from the client and put it on a message queue. And that would then, we'd have a subscriber downstream, a booking processor, and that would bring it into an event sourcing system. That worked well until one day when we had a very strange bug and we lost some messages. And we were left in a position where we were like, well, what have we lost? We don't know. There's no way of telling. We can't search it. So we then reacted by another approach, which was to write to a database first and then publish the message. Of course, that's not a great design because you've got two writes in a non-atomic operation there. So, you're left with the scenario of what if one fails and the other one doesn't fail. So that leads us on to Cosmos DB, and one of the great benefits of Cosmos DB. We can now write the request straight into Cosmos DB in the region, and then we can use the change feed processor to asynchronously pull that data back into our event sourcing system. So we've really got there the benefit of a searchable database and a queue. So now I'm going to do a demo of how we are using Cosmos DB to book a return. So before we go, I'll just explain what we're going to do. We've got an API here on the left. It's going to be writing into Cosmos DB, and then we've got a little service using the change feed processor provided by Microsoft to pull that data over, and it's going to write it into an event store. If you could push me over, thank you. And my computer's gone to sleep. Right, there we go. So this is the simulation of the screen. You've got two items that you want to return. You're going to hit the return, place return button. Now I'm going to use a console app to simulate that because a bit later on I might apply a bit of load and push quite a few orders through. So what we've got here, this is our Document DB Studio. This is an open source application on GitHub. We can use this to look at our database. We've got a collection here called book returns, and we're going to book returns into it. So using this client here, let's just see what the last ID was, 3. I'll refresh that. Okay, we've got a few, let's say 13. So I'm going to book in at the moment just one request. That's going to go into Cosmos DB. There he is. So there's our payload. That's coming in from the native mobile app. It's Robert Smith is returning a couple of products, and they're being collected from his address in London. Now, we need to do is bring those records into the event store. So we're going to use the change feed processor at this point. Let's have a look at the code. As Andrew was saying earlier, we're using the NuGet package provided by Microsoft. We implement an IE change feed observer, and we basically have 3 methods we need to implement. One is to open, the other one's to close. That's the starting and shutting down of the service. And then we have process changes async. And this is provided with a collection of documents. These are the changed documents or the new requests as they're coming in from the API. And all we're going to do is going to enumerate those documents, and then we're going to load up our event store and then append the return accepted event into the event store. So let's see this in action. We've got one here. When this client starts up, you can see it uses a lease database and it acquires the lease for all of the partitions in the collection. So we're running a Cosmos DB collection here with 10 partitions. So when this client started up, it goes away and grabs those partitions. He owns those partitions. And we can actually see he's already processed that return. So what I'll do is I'll put another one in just so we can see it in action. So that's gone into the API. And you can see straight away the other client has picked it up and saved it into the event store. So if we go down here just to show you that, over here, here's our event store. If I refresh there, somewhere in there, record 13 and record 14. Just demonstrate one other thing which I really like about the change feed processor is the scalability of it. So we might host that in a cloud service, in a worker role. We might host it as a executable in-service fabric. But at the moment, we're running a single instance, and that could die. But the great thing about the change feed processor is you can start up 2 or 3 instances, and between them, they're going to acquire the leases. So this gives you great scalability. If one of the clients was to die, the other one will pick up the work. So you can see here, this instance has started up. He's stolen the lease for partition 7, and the original process over here is now lost 2 leases. So over a period of time, I think it's about a minute, you can configure all of these settings. Over a period of time, they're going to balance the workload between them. So those 10 partitions will be shared 3, 3, 4. So at this point, what I've done is I've shown you how we can use Cosmos DB to take booking requests from a client and react to those coming in and save them into an event store. Now we're going to talk about processing those events and the life cycle of a return, and for that we use an event sourcing pattern, which Mike's going to talk to you about.
Okay, thanks, Andy. We finished the last use case writing to an event store, and this is a data store that drives the event sourcing pattern. Event sourcing models data differently to a current state. Rather than throwing the latest view of an entity, all changes to state are represented as a series of immutable events called an event stream. At the top is a typical current state model. Notice how you can't really see what's happened prior in each of these returns. You can only see the current state. So at the bottom is an event stream for a given return. And what you can see here is you've got a full audit trail of everything that has happened. Event stores use a depend-only model. You never update an event, you never delete an event within a stream. And the other benefit of this, as well as the audit trail, is it basically ensures that any database you use event sourcing with, the depend-only nature of it means there's then no write locks concerns when multiple writes are happening concurrently. With event sourcing, we can always get back to the current state anyway by replaying events in the stream from first to last. In returns management, we've got a small number of events per return stream, so replaying the events isn't really ever a concern. So event sourcing is really a key part of the architecture for both order and returns management at ASOS. So here's an example of one of our events. Our events always have a unique ID and a creation timestamp. So the reason for this is because the unique ID is then used for idempotency, so we can check if we've already seen this event before and react accordingly. And we always have a timestamp to just basically let us know, so we can analyze when that event has happened. Event data only contains the changes to states that are relevant to the event. So for example, every time we create further events from this initial return created, we're not going to repeat things like the returned products, the customer ID, because we already have those in a previous event. And what we also do here is we structure our contracts to ensure backwards compatibility. So on the slide here, we can see we've got the product array of return products. Now, we could have modeled this as an array of integer product IDs. So the reason we didn't do that is because if we needed more product information in this event, we'd suddenly break the event. And what we were finding in the past was we ended up with a lot of complexity in our system where every time we added a new field, we created a new event version. So that just created a bit of a nightmare, a lot of extra mess, a lot of extra tests in our code. So we've gone with this more simplified approach. So ASOS has chosen Cosmos DB as a strategic database technology for sourcing. The simple partitioning support and change feed make it a great database for event sourcing. Partition collections allow us to store terabytes of data, which is really key when you've got an append-only structure where you're not deleting anything. The stream ID is the partition key. Geo-replication is also used to ensure that if a regional failure occurs, we can still process returns. The event store's really our book of record. We don't really want to lose anything there. So that geo-replication gives us a lot of confidence, and it's really, really easy to configure. For consistency, we also, within the geo-replication, we also use the smallest bounded staleness to ensure that in a disaster that any data loss is kept to a bare minimum. We also use the transactions feature of Cosmos DB to allow us to write each event as a separate document. So we can actually write 5 events in one go, but they'll all be represented as separate documents, which is actually really important moving forward when we look at how we're going to give a customer-centric view of the returns. Cosmos DB doesn't provide an SDK that's specifically suited for event sourcing. We've written one that just sits on top of the document API. And that's called simple event sourcing. So I'll just show you that in action and how we build a reactive process based off Cosmos DB, event sourcing, and the change feed. So what I'll do is I'll show you a return event. So any of these should do. Actually, maybe not. Could pick this one. So what you can see here is all the information that Andy collected in his event and wrote to the event store is represented in the body here. Now, what we've done for efficiency is because we shouldn't be searching event stores, the body's never indexed. So it's only these top-level fields here that are ever indexed. So that gives us a nice RU cost-saving optimization, and it also makes the writes a bit quicker. The stream ID here, as I mentioned earlier, is the partition key, and we also have a body type, which is helpful for serialization and deserialization. So when we're building a process here, what we can do with the change feed is we have a change feed processor here, and what we're basically doing is just as documents come in, we're just deserializing the document and creating that event-centric view rather than a document-centric view. Then what we do is we handle the event, and what we're basically doing then is delegating the event over to an application service. In this case, we've just created these handler methods that act as application services. So you can see here we've just got some routing based on the message type. So we'll just drill into the return created handler, as that's the event we just looked at. And then this is really where we're starting to also use simple event store to actually then work with the event store directly. So here what we're doing is we're reading the entire stream from forward. So we're taking the first event and replaying in that and getting all the events up until the end. Then what we're doing is we're passing that to a business object, in this case a return. And what we do to hydrate the current state of that return is we just loop through all the events and replay them through these update state methods. So if I go into an example of that, you can see here all we're doing is setting the particular fields based on those methods. So once we've got the current state, we then run a command method. And then in this example, all we're doing is just doing a very basic check to say, have we already processed the booking? And if we haven't, append another event onto the event store. So all we're doing is we've just added that in memory at the moment. We haven't written it away to Cosmos DB. And then what we do is we actually then append all those events to the event store. So as I say, if we'd actually collected more than one, we could do that in one atomic write as well, and we don't have to worry about two of the writes failing and two of the events working and one of them failing. So the nice thing about this is just by using that append pan, we haven't actually had to translate anything into, say, any messages on a service bus or anything like that. The events we're writing are the events we're also using for integration between microservices as well. All we've done here is kept it simple, so you can imagine each of these handler classes being separate microservices, and the approach would just work. So let me just show you this in action. So what I've got here is this is actually the change feed observer what we were just looking at the code for. And you can see it's basically been booking some return, deserializing some events. So what I'll do is I'll just fire a bit more load into this so you can see it. Okay, so you can see the returns are being booked, and then shortly you should see the change feed process those, and you can see how these returns are transitioning between the created state all the way up until the return getting booked. Okay, so what I'll do then is I'll hand back over to Andrew, and he'll carry on. Thanks.
Thank you, Mike. So Mike has shown us through event sourcing how we have taken a return through its journey. There's other things as a system we need to do. One of them will be integrating with other systems. So a scenario here might be choreographing with other systems. As the returns platform, we aren't responsible for all of the activity. We need to book deliveries. We need payments to make the refund. And because we're using an event-centric architecture, we choreograph with people like payments. So we might emit a refund authorized event. They'll subscribe to that, and they'll go off and make the refund. So we need to integrate with these other people, and we can do that through messaging, rather than allowing them to come straight into our, to use a change feed into our collection. We can decouple ourselves through a service bus. So that's a good example. So we here in this diagram here, we can show that we've got an event publisher service subscribing to the change feed, listening to the events, and he's emitting them as service bus messages out to other clients that are interested. As part of that reading of the change feed, he might do some transformation as well. There might be some PII, some personally identifiable information that we're not allowed to emit, so it might do a little bit of transformation and remove the customer's address or something. Another good use case for this is reporting. With an event-sourced system, you have a lot of information, usually more than you'd store with a current state system. Very useful information. Right in the future, you might not even know the information you needed, so it's very useful to have all this information to hand. What we can do here is integrate with a data lake, so we can be publishing out service bus messages, and they can be received by a data lake for putting into a reporting system. I'm going to do a demo now showing you how we can do this. But I'm also going to take advantage of the announcement that Microsoft made this week, and that's around the Azure function support. So this use case here, originally we would have hosted that in Service Fabric or as a cloud service worker role. We're now going to use the Azure functions to do the same work, and we'll have a look at how it works. Okay, so I have an Azure function here, once it loads up, called Event Publisher. And we configure it to understand which the monitored database is. In this case, it's the event store. And we also tell it where to write its least, which is its basically record of where it is in the event stream. And here's the method. All we need to do is write code inside this run method here. Again, we're getting a collection of changed documents. These will be the events as they're coming in. And we're just going to enumerate them. We're going to deserialize the payload, get it into JSON, and then we're going to construct a brokered message and then send that out onto Service Bus. So for every event that's occurring within our system, we're just going to basically, we're not going to transform it, we're just going to push it straight out onto Service Bus. So that's, just check that's up and running. I'll use the log window here to see its progress. So again, if I use the client here, I shall push in 10 booked returns. They're going in. And you can see immediately Azure Functions is now processing those and emitting service bus messages. So again, it's very quick. The nice thing about this now is I don't need to worry about any scalability concerns. I don't need to worry about the hosting of it. All I need to do is write some code in this run method. And I'm not suggesting people do this in production, but you can literally change it on the fly. Let's just go and have a look at the output just to prove it's working. Here's my queue. I think it's a queue. I can't remember if it's a queue or a topic. But let's just refresh that. There's 66 messages on there. What I'll do is I'll purge it just to show it properly working. Why do I have a wait button? Right, it's down to 0, good. Let's refresh that. I'll push some more orders in. So those are going in. Azure Functions should be picking those up. There we go. Processing various events. And then we should see, if I refresh this queue here, 28 events, because we've pushed in 10 orders, but of those orders, there's multiple events as they're being processed. There are 30, three events per order. So we can look down here. Let me zoom it. There we go. You can see various, the payload down there and the various events coming in. So that's Azure Functions, really. Very useful. It's an alternative method. Depending on your use case, you can host your change feed processor in something like Service Fabric as a guest executable. You can use other mechanisms. It can be as a container, or you can use Azure Functions. It gives you great choice and great flexibility. Now Mike's going to talk to you about how we can change from a return-centric view in Cosmos DB to a customer-centric view.
Okay, so thanks again, Andy. Now we'll discuss how we can project event streams so our customers can view their returns. Event stores, as I mentioned earlier, aren't designed for querying. While Cosmos DB does allow this, the problem you'd run into is each event has its own schema. So the resulting queries would be really, really complex and therefore have a very high RU cost. We also want to get data as near to our customers as possible to deliver a great customer experience. So how do we solve this? So what we do is we create a subscription on the change feed, and based off that, projects those events into a read model or materialized view. The read model can use any technology you want, so it could be Cosmos DB. It could be table or blob storage. In this instance, what we're going to go through when we get to demo is blob storage. We can delete and rebuild the read model at any time as well. So this is a major benefit of having the full audit trail. So we could also use this pattern to solve the reporting problem that Andy mentioned earlier. So by having the full event store, we can just say if there was some missing fact and we wanted to reproject that from the beginning of time, we could just delete that old reporting database and replace it with a new one. So with this pattern, the query load that's coming in through the customer returns API does not impact the event store and vice versa. And this basically gives us a predictable RU usage on the event store. Read models will always be eventually consistent because basically when the events have come into the event store, there's going to be some latency between getting that back into your read model. So just bear that in mind when you're designing your systems using this pattern. But for customers understanding the status of the return, this doesn't cause any problems. So a customer's not going to be too bothered if they're waiting, say, half a second or even a second for the return information to be updated. One of the other things I've highlighted here is we've got geo-replication going between two regions. So if you've already got the event store geo-replicated into the second region, the North Europe region, you can also avoid egress costs just by subscribing to the nearest Cosmos DB instance, as long as it's in the same region, obviously. So I'd like to just give you a quick demo of how we project into a read model. So what we can see here in a moment is we have a simple representation of a returns screen. And you can see all the customer returns that have gone on, and what's actually been happening in the background as we've gone through the presentation is the read model's been constantly updated, and that's why we have so many returns to this customer. But if I use a different customer, then you can see they've only got the one return. So the way this works is if I just go into the code here, we've got a customer returns projection host with, again, another change feed observer. But this is actually quite a bit simpler than some of the other, the demo I gave earlier in terms of logic here, because all we're doing is grabbing hold of the event. We're reading the current view of the read model for that customer's returns for blob storage. And then what we do is, based on the event, we then just update the particular properties from that event So you can see here, return creator's got quite a lot of properties, and the structure of the fields is very different. So the whole point is with the materialize view pattern, we can just tailor the remodel to suit the view rather than suiting the original data source. So you can see here, delivery but and refund authorized actually just update the status. And then based off those changes, what we do is just write that back to blob storage. Now, there's no logic here whatsoever to say, oh, what happens if we get delivery but rather than return created first? But the reason for that is because with the change feed, as long as all your documents are in the same partition, you get an in-order guarantee. And because our stream ID is the partition key, it always means for a given stream, everything's going to be in order. So it makes writing these remodels, or as I say, potentially going over to any other feeds, really, really simple because of that. Otherwise, we would have had to there'd be a lot more complexity to this code. And then, as I say, all we're doing is pushing this back into blob storage. So if I just show this in action, then again, I'll just push some more returns through. Yeah. So we've got the yellow customer return projection host, which is the code I was just showing you. So you can see this has been churning away through the talk. And what I'm going to do is put some returns against our other customer. And let's just push 3 through. And then you can see that's just gone on. And you can see all the different statuses are being projected through as well. So what we should see here is, there we go, we've got 3 extra returns there. So that was it, very simple. So I'd like to hand back over to Andy now.
Yeah, I was just going to say a couple of things on that, really. Why do we do that is because, why do we need to re-index? Because when you're coming into this screen, you're based on a customer ID, and if you didn't have a reprojection in this nature, you'd end up calling the system and saying, give me return 12, give me return 46, give me return 45, give me return 47. So it'd be quite a slow query. It'd be a very slow query. The other thing I was going to mention was, with the change feed processor, by default, it gives you up to 100 documents in any one go before it checkpoints. So it is possible that you can get 100 documents and do work on 50 of them, and then your service dies. The change feed process is great because when it restarts, it'll start 50 records ago and restart, but it does mean your projections need to be idempotent because you could get that same event twice through failure. So you just need to be very careful about that. If you're doing things like, in our scenario, counting order values, there's a transactional concern there. You can do things like you've got options on the change feed processor. You can set things like, how often do I checkpoint? Is it every document? Is it after a period of time? How long do I hold the lease open for? So it's a nice little piece of code from Microsoft.
Yeah, but in this example, worst case, all that would happen is if we replayed some previous events due to failure, we'd get a bit of rewind in the return history, which, to be fair, the amount of times the customer's checking the return is probably not that significant. So it's all about the trade-offs given your particular problem domain.
We've talked a lot about orders and returns. Cosmos DB is finding its way around Datos even more now. It's being used in pricing, I think, as a stream of price changes. I think we're using event sourcing there, so as prices are being changed, we can keep a history of those changes. Very important when you're doing things like FX. It's being used in recommendations as a low latency key value store for being able to present to the customer what are the recommended items. You've bought some red shoes, perhaps you want some green shoes. It's being used by payments as well in the latest system, and it's also being used by saved items. So when you're in checkout, but you're not quite ready to buy, you save it. We're looking at using it there. I think to conclude from ASOS's perspective, we like Cosmos DB. It meets the high scale demands. It's the geo-replication and the SLAs. The change feed enables scalable, simple event sourcing, which is very important, and Azure Functions is a great new way of looking at perhaps more ad hoc, more reactive changes that we can use to perhaps do some reprojections, maybe not in production, maybe for reporting or other things like that. Oh, that's a little bit too early. I think we'll hand you back to Andrew at this point.
So I am asked to do a reminder that, we value your feedback. If you liked our session, please, leave us some feedback on an evaluation. If you didn't like the session, then please maybe come talk to us instead. But anyways, thank you very much for coming to our talk, and we're going to open up the floor for Q&A. We have a few microphones here if you'd like to ask questions, and afterwards we'll also have a chance if you want to come up and come chat with us.
And yeah, I'd say have a go with Cosmos DB, have a play with the change feed processor. It's a really good, it's good.
Cool. Are there any questions? Can we come up to the microphone so that everyone can hear?
How do you guys, it looks really good, but how do you guys get all this implemented within a unit testing environment for end-to-end tests of all the communications and events and change feed? Is change feed supported on the document DB emulator yet as well?
Yeah, yes, it is. Document DB emulator works with change feed. From the unit testing perspective, that's quite the good thing about event sourcing, because actually we can break down our overall architecture into very small state transitions, given a refund authorized refund, So it makes it a lot easier to unit test. Also the handler logic, the fact that we can start from a defined state, be given an event with data, and then transition to a new state. So the decomposition of that testing makes things much, much easier.
What it's also worth mentioning is if you're using the simple event store NuGet package, then what we actually do is we provide an in-memory abstraction, and we basically run the same unit tests against that we run against our Cosmos DB implementation. So if you're basically writing a unit test, you can actually just subtract the Cosmos DB implementation for the in-memory one. So for reading and writing, that's great for unit testing and isolating your code that way. If you're writing something off the change feed processor, then what I'd probably recommend you do is write something, you basically abstract the usage of when the documents come in, because certainly from my experience, I've not seen a clear route yet where you can unit test by just creating a document from scratch. It has to go to Cosmos DB to go through the feed. But apart from that, to be honest, we haven't had too much issues, and because we're a microservices architecture as well, we can generally get a lot of confidence just in each of those components. So there shouldn't be too much of a need to have that many tests exercising the whole end-to-end journey here.
Thanks.
Cool. Are there any other questions?
You talked about a few things that you do to have kind of like reliable data and things like that. In your guys' experience, what was like maybe a failure that occurred and what you had to do to mitigate it going forward? Like data loss or system unavailability, hardening?
We haven't had any data loss yet. We did have one issue once where we had such a large document, the indexing was a bit slow. It was because I think it was, and that was probably through the failure of not choosing to be a bit more selective with our indexing. You had hundreds and hundreds of properties, and behind the scenes, the Cosmos DB is going to try and index every property to make it searchable. I think that's the only one issue we found.
One of the nice things about Cosmos DB is when I mentioned those partition sets, each partition set is actually replicated across 4 physical replicas spread across different fault domains in each individual region. As a result, you have a high amount of redundancy, so that even upon disk failure, what we do is we automatically tear down that replica and bootstrap an additional replica. And each time you produce a write into Cosmos DB, what we do is we're actually durably getting a commit on a quorum of replicas before acknowledging that write. And so this is why we're able to actually provide a high amount of resiliency around data durability. And as Andrew mentioned, one of the things you do want to take a look at is the indexing policy. We have a unique capability around automatic indexing where we can automatically index every property of every record. This works well when you have tens or maybe even hundreds of properties. However, if you have, let's say, thousands of properties or even more than that, let's say you're jamming in 2 megabyte records with 100,000 properties, chances are you're not going to query across all 100,000 properties, so you might want to narrow down and selectively index a set of those properties.
Yeah, and I think Cosmos's connection methodology got better than what Service Bus used to have, where high availability meant 2 connection strings and having to be smart about it, whereas I think you guys have more like traffic manager type setup.
Yeah, that's correct. We actually stuff all of the different geo-replicas under the same URI, under a multi-homing API. And what's kind of cool is the client, when it connects, it uses a single URI. So if you have to do a failover, you never have to do an application redeployment. Instead, what happens is the client actually becomes aware of the global topology, and you can actually set a failover policy and priority list of what are the regions you want to fall back on in this list. And then the client will automatically handle that for you. So you never have to do any kind of app redeployment whenever you're doing something like disaster recovery.
Cool. And then you touched on it as far as the eventually consistent and having the UI respond to it. Was there any other learnings you guys had as far as like, hey, I say something and for whatever reason it takes a second or two to get through and the UI is still waiting on the response? Any other learnings there?
Well, I think generally it depends on your UI use case. So we don't typically use eventual consistency where the expected response. It's for the read model type of projections where a customer isn't waiting that long. So for example, when an order's booked or return's booked, we saw essentially Andy was using immediate consistency by just writing straight to the event store. So he could provide, if that was abstracted over an API, then, which it actually was in the demo, then the customer would get an immediate response. So it's just about the trade-offs for your particular problem scenario. But what Cosmos DB has been helpful with that is just being able to, as Andy shared before, being able to deploy different Cosmos DBs and then sort of feed that through into a central one for processing.
And I think also we're always playing this consistency, availability, eventual consistency, immediate consistency problem. So another scenario we've had is, well, I'm going to publish out a return accepted on a service bus to another system. He's going to immediately come back and try and ask for that. And if that API is eventually consistent, because it itself is being projected from the event store, it might not be ready. So at that point, we're deciding, well, actually, maybe we should have an API around the event store for immediate consistency. So if that message is going out, he's guaranteed to get it. Or we've got to bake in some kind of retry semantics into the client. Perhaps when the message goes out on the service bus, it has a version number against it. When the client comes and asks for that data, he submits the expected version number on the incoming request, and the API, if it's eventually consistent, says, no, sorry, I'm not up to date yet, come back half a second later.
One question, like when you mentioned you this function, why don't you, using web jobs, is there any particular reason?
At the moment, our hosting strategy is we're currently on cloud services. We're looking to move to Service Fabric for all of our services. But at the moment, the Azure Functions has only come out this week, so it's another option for us. I think we're likely to stay with Service Fabric in the short to medium term and maybe use Azure Functions for some of the non-critical flows, so more the ad hoc stuff. So if somebody asks for some, maybe a projection about a particular use case, we could use Azure Functions to very quickly generate that.
The trade-offs here is really Service Fabric gives you a lot of convenience around actually handling a lot of microservices and giving you a lot of durability around that. So as it scales out, it also can help you maintain state and memory, and it can do things also like the logic around sharding this across multiple machines, and if a machine goes down, automatically bootstrapping another one. With that said, if you want to just build something that's very, very quick and optimized for speed of development, then Azure Functions allows you to actually just drop a body of code with minimal effort and then just hit run. And you even saw with Andrew when he went to the Azure Functions UI, you can actually do live changes on that code. So depending on whether you're doing a mission critical workload versus something you want to actually be able to just get something done very, very quickly, both Service Fabric and Functions give you a complete toolbox for managing this trade-off.
Absolutely, totally agree.
Okay, so price-wise, does Function cheaper compared with web jobs?
Pricing is actually about the same. At the end of the day, they're both dependent on the app service that you're hosting it on. And so Logic apps, web jobs, Functions actually all have the exact same pricing model.
Okay, so it's basically provides serverless.
It provides a serverless container for your functions so that you don't have to basically build all that scaffolding around, when you want to just run a small unit of business logic.
So, quick question here. You have, say you're replicated across 3 regions. One is your write, the other 2 are your reads. You have, whether they're functions or microservices or service fabric, across those 3 regions as well. There's a single URI for the database, correct?
Correct.
So all 3 of them are pointing to the same URL, so the client itself knows when it's going to write, that it's going to go to the write region, and it's going to read, and it reads from the local? How does that work?
Yeah, so you can set a preferred location. So you can only ever write to one place,
Right.
and it will flip if there's a failover. That's all automatic. But you have the option on reading. You can set a preferred location,
Okay.
which in the eventually consistent model, the read APIs, you're more likely to set to be locally. That has an advantage as well in terms of RUs, because you're using the RUs locally. You're paying RUs every time you hit this database, and on the writer, you're going to be doing a lot more work than you will be. So it gives
So
you
the
the
client
option.
takes care of the write. You don't have to say, okay, you have to go to region 1.
No, you set exactly. You set the preferred location for reading and the writing.
Okay.
You set up in the connection string all of the services.
I mean, what's also worth adding to that is if you're using Cosmos DB as an event store, then you won't want to use the secondaries for reading there. That's more for basically a secondary backup. Now, the reason for that is because if you read a stale stream, you're very likely when you're appending to that to get concurrency issues. So just bear that in mind, that we're generally using it more for using secondary regions to optimize read throughput.
Here's what the code snippet looks like. You have a single URI that the Cosmos DB or the application will connect to Cosmos DB. And upon startup, it's going to get a complete topology of what are all the active regions. And it's actually going to periodically refresh those regions as well. And what you're also going to do is you're going to set a list of preferred locations like this. And you're probably going to want to have this app config driven or environment variable driven. So you deploy the same code base to each of your regional functions or regional application instances. It reads from the environment variable, understanding, hey, this is the location that I'm in. So I want to actually always connect to the regions closest to me. And that way, your West US application instance might go from West US to East US to Europe, while your Europe app instance might go from North Europe to East US to West US, like a completely different order.
Hi, I have a question. So based on your working experience with Cosmos DB, are there any differences between the reads and the writes in terms of performance? And if there are, what would be like some mitigation strategies? I don't know, for example, like replication or stuff like that, like read versus write?
So the performance guarantees around Cosmos DB, we actually are the first database service to offer a P99 latency guarantee around it, meaning we actually try to give you predictable performance around it. For write performance, if you were to use a typical 1 kilobyte record, you should see about 15 millisecond latency from the time a record comes into Cosmos DB to when it gets replicated, gets a durable quorum commit, and acknowledges. All of that will happen within 15 milliseconds. For read operations, if you're doing a read on that same record, let's say a 1 kilobyte record, what you'll see is less than 10 millisecond read latencies. The latencies are fairly comparable. I mean, when you're looking at like less than 10 and less than 15 millisecond latencies, at the end of the day, you're still dealing with a very, very short amount of latency. So there's not really a lot of concerns when you're thinking about reads and writes. The thing that you want to think about is once you get into more complex queries and making sure that those queries, there's actually some best practices around routing the queries, ideally to a particular partition. However, when you are doing cross-partition queries, we actually do have a lot of knobs and levers for you to tune in terms of actually controlling the degree of parallelism that it tries to fan out the query, as well as managing a prefetch buffer for also speeding up a cross-partition query.
Okay, thank you.
Another one is right on the change-free processor. So you have a replica that's set for write, 2 or 3 read replicas for availability. Does the change-free processor return the same data on each of those replicas? Take, for example, something, you have your processor processing the change feed on your write replica. and that replica goes over, automatically gets switched over to one of your read replicas, does it start getting the same changes that were already processed?
So it depends how you tune it, and you can actually configure it in both different manners. Basically, it's how you manage the leases. For the change feed, what we're doing is we're actually exposing the records via a log sequence number on the underlying store. And so basically, when you attach the change feed processor to the change feed, you can actually say, hey, this is a log sequence number I've observed, and I want to start from there. Or I can start from any other point.
Okay, so you basically need to keep track of that lease number somewhere.
And basically, the change feed processor library that we've released actually does all of this lease management for you. So on any given host, as long as they have the same set of leases, if you're attached to the same lease collection, then all of the hosts can actually share those leases. And this is how you can kind of like divide and conquer by scaling out a large number of consumers.
Okay. And that lease is per collection?
Per partition, underlying partition, yeah.
Okay. That doesn't work with table storage per chance, does it?
So the future of table storage is we're actually on a roughly 1-year journey to actually change the back end of table storage onto Cosmos DB. And as we embark on this journey, this means that you'll see secondary index support, lower latencies, higher throughput, as well as change feed support on table storage. You can preview it actually today through the Preview Tables API, but we actually are on a journey to enable this for all of table storage existing users.
Just one question regarding they have slides saying the best practice, the design or good partition key. And you particularly mentioned for write, I understand the ratio of the insert versus update. So how does that impact on which partition key?
Gotcha. The insert versus update has a strong impact on the object model, which then in turn might also impact how you define the partition strategy. But the large impact is actually on the object model. And what you want to avoid doing is, well, actually, I'll kind of, to summarize this, when you normalize records and you shred a record into many small pieces, you're actually really optimizing for updates. You're reducing the need for having to fan out and update. You're also reducing the need of touching basically a very small portion of a very large record, which will basically have a higher RU cost for updating. When you consolidate everything into a single record, some of the benefits are you can actually just do point reads on that and grab the whole data, exploit data locality, both for when you insert as well as when you read it back out. And so depending on whether you are update heavy or read and insert heavy, this changes your object model in terms of whether you want many, many small grain documents versus very, very large documents.
Okay. So basically, the key is just the dynamically design your object module.
Yeah, basically the whole data model partitioning strategy, all of this, you want to have that follow your particular scenario and workload. So this is one of actually the key things to consider when you're moving from, let's say, a relational database paradigm. For relational databases, you always think about entities first, and you always try to normalize everything. For a distributed database like Cosmos DB, you want to actually think about your scenario first, your workload first, and use that as the North Star for how you design both your object model and the partition strategy.
Thank you.
Cool. I think we are out of time, but if you want, we'll be outside, and if you want, you can come and chat with us. Thank you very much for attending.
Thank you.
Thanks.